doing? Hopefully the volume is going okay. Starting a little bit early today. See if I can get some people on. And what I'll do is I have a presentation I'll do on Tuesday for my astronomy research class. So I'll actually present that to you all. See if I can get some feedback. In the meantime, I'll work uh, some electrodynamics problems and get some practice going on there. So we'll see who shows. So perhaps what I'll do is, so that's what the presentation will look like whenever we get started. Is up and ready to go. And this is not the main one that I'll have finished next year. This you could say is the preliminary one. But I'll make some improvements that I'll speak about at the end of the uh, presentation and get it worked out for a big presentation at a conference in March. So the goal is to get a very thorough, or at least more thorough investigation done by March of next year. I guess technically by February. So they have to send the abstract in by February, I believe. Hopefully, I can update it a bit before the final date, and then present it in March. So, but in the meantime, I'll get started with some uh, electrodynamics, electrodynamics until some folks show up through the solutions up. So this one says suppose a conductor has a cavity inside, and there's a point charge somewhere in the cavity. Prove that the net charge on the wall of the cavity must be negative q. So basically, we have um, we'll draw the conductor like this. One thing to know about conductors is the electrons are free to travel about the body. So basically, the electrons or charges in the material, the atoms sort of share the same electrons. So what happens is there is a sort of conductive zone, and then there's a non-conductive zone, and we can say that in conductors, the electrons can very easily move from this zone up to here. So it takes very little energy uh, to move them up to this conductive zone, and they could just move freely back and forth. So what that means is, since these charges can move very freely, if I were to put a positive charge in the center of this thing, since the charges can move very freely in this material, all the positive charges will run away. And technically, they're not really positive charges, but that's how we sort of describe it. The positive charges will move away, and the negative charges will attract to the positive Q. So it'll end up like this. Um, the proof, let's see how they describe it as proof. So we know we have Gauss's law where we have the flux is the integral E dot dA equals charge enclosed over epsilon naught. And if we have a situation like I've drawn here, this is Q, positive Q. So this will be negative Q. at the least. Um, because all the negative charges come closest, there have to be positive Q on the outside to balance that. So in the end, we will still get an electric field as if from that charge. So basically, if we put a Gaussian surface right there close to the surface, we'll get that electric field from that positive charge. Uh, and what that always means is that within the body of the conductor, the electric field to be zero. So there's no electric field here because there's no charge there. So within the conductor, there's always no electric field. You can say, since there's no charge in the inside here, hence no charge or E in center of conductor, Q negative must balance Q, so net Q equals zero. So the net charge at this Gaussian surface is zero. It has to be because it's a conductor. And do we have a positive Q on the inside? We must necessarily have a negative Q on the inner walls so that the net charge is zero and it satisfies the fact that we have zero charge in the middle, a zero electric field in the middle. It says then hit the net charge. How do I bring this forward? If the net charge on a conductor is Q naught, what is the net charge on the outer surface? So since these two must balance out, the net charge Q naught must be on the outer surface since there's no electric field in the middle. So since there cannot be an electric field in the middle of an actual conductor, if there's a net charge of Q naught, it must be on the outside, so there's no electric field in the inner satisfied. Which means that if we did add a Q, it'll end up being negative Q then plus Q and Q naught on the outside if we add an additional charge to that plus Q. Easy enough. Next one, we have a parallel complete capacitor. Let me just copy this thing. And area is A, distance is X apart. If the lateral dimensions of the plates are much larger than X, so this is definitely not at the scale drawing, but you can imagine the plates are relatively infinite compared to the distance between them. The capacitor is charged to potential V naught with a battery so that the plates carry charges Q and Q naught. Is plus Q and minus Q. The battery is then disconnected, so it still has charges plus Q and minus Q. How much work must be done by an external force in order to increase the separation a small distance from x to x plus change in x? And what is the change in energy? Change in final minus change in initial. All right. So they give us the answer. That makes it easier, definitely. So we have D, change in D, uh, equal change in X. So X goes to X plus change in X. Um, First thing comes to mind is the work integral. I don't think this will be directly involved here, but you know that we have this integral. Well, work is going to be the dot product of the force and the distance over which the force is applied. Let me see if how this plays a part. Like the work in this case is the same thing as the change in internal energy. So I didn't think we'll use that, but it's good to remember it. So capacitance equals, pretty sure it's Q over V, and it'll also equal A epsilon naught over D. So capacitance will be the area divided by the distance. So the bigger the area, the more capacitance, the smaller the distance between them, the more capacitance. So now we're going to keep the same amount of charge, but increase the distance. Increase the voltage. And we know it's going to have to add some energy. So the equation for the internal energy of a parallel plate capacitor, U equals Q squared over 2C, which equals 1/2 CV squared, which equals 1/2 QV. And let me see if I did remember that correctly. C equals Q over V. So replace C with Q over V. That is Q times V. And what we can do is go ahead and substitute C for this C here. So it equals Q squared over 2A epsilon naught D. We know the distance is going to be Q squared X 2A epsilon naught. So we change would end up being changing U equals U X plus change in X minus U X equals Q squared over 2A epsilon naught, and that's change in x. It's going to be x plus change in x minus x. That's change in x. And that's going to also equal the work. So the work is going to be the change in energy. And it seems to be what they have. And welcome to join and drop a line. Maybe I'll try to get one or two more and I'll do the presentation. I plan on doing this presentation here, talking about the Praesepe stars. Maybe I'll do one more electrodynamic problem, then I'll go ahead and get started on the presentation, ready or not. And if those who don't see it live, perhaps you could just give me some feedback if you watch it later. And depending on what this problem is, let's see how hard this next problem is. The 4.5 derive the energy in a parallel plate capacitor starting from the electric field density. So we're starting with electric field density E equals, oh, let me go back to the here, electric field density E equals epsilon naught 1/2 E squared. We have that E equals Q over A epsilon naught. So to come back to this one, remember these equations. Pretty sure my way was a whole lot better. Let me show the presentation that'll be coming momentarily while I look up what I did before on this problem before I move on from it. Go ahead and drop a line if you hear. This is what 4.5. See what I did before. So look at the steps that I did before. Hopefully I don't get a problem like this on the exam, the final. So we're starting with the electric field energy density equals 1/2 epsilon naught E squared. And the energy equals the electric field energy density times a volume. So this is similar to how uh, charge is a per surface density times an area, or a volume density times a volume. The energy, electric field energy density It's sort of like this density here. We multiply it by volume, we get the energy. So I can go ahead and do 1/2. So, oh, let me switch back to the regular screen. I'll start the presentation momentarily after I finish this problem here. We have 1/2 epsilon naught uh, e squared, and the volume will be the area times the distance. So basically, we're looking at the volume between these two plates. It says the area of the plates and the distance that'll give the volume of that whole space. So it looks like what I did from here, I remember that E equals sigma over epsilon naught, which equals Q over sigma A, which is what I was looking at over there, uh, uh, the sigma and the A. So basically, if I solve for sigma, that's Q over A from here. So then we have that equals 1/2 epsilon naught Q squared over epsilon naught squared A squared, then A times D. So you can actually cancel one of these out and cancel one of these out. And that should be 1/2 Q squared D over epsilon naught A. That looks good so far. And remember that C equals Q over V. So Q equals CV. When I plug that in, we have 1/2 C squared V squared D over epsilon naught A. That looks good. And the last thing we have is C equals V over D, which equals epsilon naught A over D. So we have remind myself how I substituted this one in. Oh, I see. So we have epsilon naught A over D. That's C in the denominator. So we end up with 1/2 C squared V squared over C. So that equals 1/2 C V squared. And I believe derive the energy in a parallel plate capacitor starting from the electric field density. All right. We have that equals U. So that's the energy in a parallel plate capacitor, which will deal with the capacitance and the voltage going through the plates. All right. So I believe that's another homework down. And I'll go ahead and start with the presentation. And should only take 15 minutes, but I'm not supposed to take more than 15 minutes. Gotta try to keep it 15 minutes. And maybe I'll call it in or do another problem or two. So at this point, I'm up to homework. I'm on homework 5. So I may do some homework for our problem. Maybe some more people to show up for the presentation and give me some feedback. But I'll just make a note that I'm on homework 5 so I can have that there as a note for myself. So let me get my timer started from our presentation. And those who are watching, you can prepare some questions that you might have. And I'm looking at the wrong one for the timer. Here. So here we go. Remember, I want y'all to give me some feedback, whether in the live chat there or as a comment on the video later. Y'all let me know what y'all think about the presentation. If you have any questions or something is unclear or anything like that. So my name is Darrell Lee Berry Jr. And the current research I'm doing right now is on stellar mass as a function of rotation in the Praesepe star cluster. So basically, what I'm doing is I'm looking at how the rotation in mass is distributed in space in the cluster. This is an image of the Praesepe cluster here, taken by Lauterbach in 2022. So as you can see, it's a beautiful cluster. It's not necessarily shaped in such a way as like Pleiades, which is a very popular known cluster, with the seven stars or seven sister sets there. But this cluster does have several interesting characteristics. Few mega uh, years old. It's in the Cancer constellation. It's been known since BC times, and so basically, what I'm going to do is, at least what I've done in my research is, the first thing I did was take a look at the rotation of stars. So those who saw any debates I did, you saw probably saw I mentioned this before. The image on the left is an image I took of the sun from August the 3rd. And if you look at the image on the left, the image on the right is an image from the Atmospheric Imaging Assembly and Helioseismic and Magnetic Imager on one of these satellites that's studying the sun. So there's many different satellites in space, of course. And I went ahead and fished out the image for the particular time that I took my solar image. When you look at that image, you can see that these sunspots or the star spots on the left image matches the areas of high solar activity on the right image. And this is basically the origin of sunspots or star spots. There's these magnetic arcs of energy that arc out of the sun and arc into the sun. And that's why star spots or sunspots occur in pairs, where the magnetic field comes out and comes in. That causes a cooler area on the sun, and we could observe it on the sun because the sun is close enough. We understand that all stars have these dimmer areas or cooler areas that they call star spots on distant stars that correspond to periods and areas of high magnetic activity. If you look at the top image on the right, this is one of these stars, the light curves of one of the stars in Persepi, where if you look at the solar image, you can see how the spots on the sun dims the overall light of the sun. So we can study stars that are distant stars away from us and see how there's a periodic brightening and dimming of the light. And if we study that, take notes of that brightening and dimming like we see on the top plot on the right, we can actually apply algorithms and capture the period of that brightening and dimming. And that's what we see at the bottom. The period of that star, the rotation is about 1.59 days, looking at the period about which the brightness and dimming occur. So the foundation of my rotation aspect is looking at the period of rotation. I also mentioned masses. The masses were actually gotten to by processes that I didn't do myself, but dealing with magnitudes, the brightness of the star, K2 magnitudes, and a process of deriving the magnitudes from that because we understand main sequence stars well enough to have a good understanding of the correlation between the brightness of the star and the mass of the star, the size of the star. Interesting thing about Persepi is it's composed of relatively young stars, so it's an open cluster. There's many different types of clusters, or at least several types of clusters. And an open cluster, which is the type of cluster that Persepi is, composed of between a few dozen or up to tens of thousands of very young stars, which means that they're all main sequence stars, so that this understanding of relationships between mass and luminosity and magnitude is very consistent. That's why we was able to derive the masses of the stars, and I'll show that a part of that in an upcoming slide. So one of the first things I did was I recreated one of the slides from the main paper I read by friend Polly and her team. So basically, what they did was they took slides from data from K2, Kepler 2, we can mission as Kepler 2, and they used that to get the light curves to get the rotation data. I simply recreated one of those plots to confirm that I had the proper data. After I confirmed I had the proper data, I started to plot various ways the actual stars in Praesepe. So if you look at the plot on the top right, that's basically the entire uh, uh, cluster of stars, and the expanded one on the left, I sort of zoomed in on that central area. We can get a better look at what the stars look like. And one thing I'll point out is in my plots, I scaled up the sizes of these stars. So if you look at the sizes of the plots, the dots show you the regular size or the relative sizes of the stars. The stars range that was in this study range between 0 solar masses and 1.6 solar masses. So if you look at it, if you see a small dot, that's a smaller star. You see a larger dot, that's a bigger star. But I multiplied it by about 100. Also, otherwise, they will all just look like point light sources. So the sizes of the stars are amplified. Plotting those masses per period of rotation gives an interesting distribution. You can see that very low mass stars have a very short period of rotation, which means they rotate very quickly. The same as very high mass stars. Looks like around the 0.4 solar masses, the the rotation peaks at its lowest point. And note that the masses are in bins of tens of solar masses because that's the most accurate assessment that we can make right now with the data that we have with magnitudes and things like that. And one of the things I did was, if you notice this plot here, it's in degrees declination on the y-axis and distance. What I did was I converted it to uh, coordinate Cartesian coordinate as suggested by my mentor, and using the equations at the top, standard spherical coordinates. Also did a shift of the coordinate system to about the center of Praesepe, and also found the center of mass of the stars in Praesepe and placed the origin at that center. I just found that I can't remember the exact error, but I was getting some kind of error when I was trying to actually calculate the placement of things with the actual center of mass coordinates. So I reverted back to the just the regular visually. Basically, I just visually looked at the middle of the axes and picked that point to be the center origin of the x and y axis, and that actually worked better for my actual analysis. But you can see at the top the actual equations that I utilized to get the center of mass. And the center equation, the right equation is for the center of mass. The center equation was simply the shift, whereby I simply looked at the center point of the where things are located on that axis. I got that midpoint, and after I masked out data that was not relevant, they had some data, some stars that were missing rotation data, for instance. Excluding those stars, I had 1,012 stars that I shifted so that the axis is in the center of Persepi. What I ended up doing was I ended up uh, trying to switch it to back to spherical coordinates within Persepi, but I had difficulty doing that. The graphs were not turning out properly. I later realized it's because the center, the origin, I'm dividing by zero. So I have to work on how to do that in the longer term. In the short term, what I went ahead and did was actually cut Persepi. I stayed with the Cartesian coordinates in the general center of the cluster, and I divided the cluster into several slices along the X, Y, and Z plane. So I can simply find out the concentration of lowest period of rotation and the concentration of highest mass in those slices. Those basically, you can say, rectangular slices in Praesepe. So if you look at the uh, uh, larger plot here, you can see that the lowest period of rotation is in as we plotted it here on the YZ plane, the upper right, and the concentration of highest average mass is in the left. So the contrary to my expectations, these concentrations of mass and rotation are sort of all set from the center, which means that the masses and the concentrations of rotation and mass are highly asymmetrical. And if you look at the red shaded part, you can see how in uh, legend for the rotation, the lighter shaded blues or the shorter period of rotation, so it rotates faster. And if you look at that that shaded area, you can see there's a lot of light blues there. And if you look at that green shaded area, you can see that there's three nice sized stars that are within that same area. So basically, in all the other slices, there was a blended, enough of a blend of high mass and low mass stars, or high rotation and low rotation stars, that it averaged out, so it wasn't a high concentration. So my findings in the end was that the distribution of mass and rotation is quite asymmetric in stellar clusters, which is contrary to what I would expect it. Also, the highest concentrations of rotation and masses are not in the same location. I actually thought that the highest masses would also carry the highest rotation. Going back to the previous slide, it is generally the case that higher massive stars rotate faster, but they don't necessarily congregate in the same places like I expected. So they're distributed quite randomly. So what I plan on doing in the future, the improvements I'll make, is I'll work out centering the spherical coordinates again, uh, basically converting back the spherical coordinates from the centered Cartesian coordinates. I have to figure out how to do that without messing up the graph dividing by zero. I noticed that when I was cutting the Persepi into slices, the more slices I cut it into, it seemed like the data was duplicating a bit, so I need to work that out. And also, when I figure those things out, I can work the analysis on multiple clusters and do comparisons of distribution of multiple clusters and see how that works. So y'all can let me know what y'all think. That was my presentation. Good practice run. I'll probably sharpen up some things and I'll give the presentation again on the third in front of class. And but that's pretty much what I'll be talking about and what I'll be discussing. I think I'll go ahead and call it here. I'm about halfway through. Did a few electrodynamics problems and I did a presentation on Praesepe. So still in the holiday season, so it seems like a lot of people busy. But I'll look forward to seeing y'all and miss seeing y'all today. Hopefully I'll see y'all next time. Those who catch it later, be sure to give me some feedback on the presentation. Anything I can make clearer, anything I can add to the slides, remove to the slides, or change around, or what have you. And I'll be here the same time next week. And by the way, I haven't heard back from that. I guess I assume he's a flat earther trying to say that there's no pictures of the globe. If you're watching, like I said, let me know when you want to talk. I'm here every Saturday. But I notice these people, they're usually most of them are just keyboard warriors. They just come and just spew their nonsense in chats, but they don't want to actually be challenged on the stuff they believe because it's just a delusion that they need to just spout out and run. So I know this is very rare for them to actually want to talk and back up the stuff that they're saying. So this is surprising me if that person just disappears. But if you're here, just let me know when, and we can go ahead and talk about what you're saying. There's no actual pictures of the Earth. It's awesome. I'll see y'all next time.